All right, welcome to Chapter 8, which is Applications of Definite Integrals. The very first section, 8.1, is just all about net change. We're talking accumulation here. How much does something change? It is a bunch of examples, and all I'm going to be doing in this section is banging through examples. I'm going to try to make several short videos, one example per video. I'm going to introduce the basic idea here and do two quick videos, and then we'll just start moving on through these examples. So the first thing we need to think about is how do I find an accumulation? And the difficulty, of course, is we've got these integrals, and what we need to do is we need to think, okay, where does this integral come from? So if we think about the sum of some function multiplied by the width of the rectangles in that function, we add up all these rectangles and we get an accumulation. And it's a pretty decent approximation, or can be a decent approximation. Now, if we take the limit as delta x goes to 0, what we get is we get the integral from the beginning to the end of the same function, and this is an exact value. So sometimes it's helpful to just visualize, well, what's going on with this, so that we can then write a good integral. If we try to go straight to the integral and say, oh, well, we'll just stick the function into the integral, it doesn't always work very well just because of the nature of the functions. So let's look at a couple examples. First of all, we've got some function, and we know that the rate of change of position with respect to time is velocity, and we're told that this is t squared minus 8 over t plus 1 squared. The function looks something like this. And if we think about what's happening here, when velocity is negative, we're moving to the left. And because it's getting closer to 0, we are slowing. And when velocity over to the right here is positive, we know that we're moving to the right. And because it is increasing, we know that we are speeding up. Now, how far do we move? Well, we know that we're going to move at some time a minus wherever we started, and that's going to be the sum of the little velocity rectangles. I'm going to make these little rectangles. And this is a displacement. And how do I know it's a displacement? Well, these rectangles are going to be negative, which means I'm moving to the left. These rectangles are going to be positive, which means I'm moving to the right. And when I add these all up, what I'm going to get is a displacement rather than a distance traveled. So thinking about what we said at the beginning, we take the limit as delta t goes to 0, and we can say very simply that this is the integral of the velocity with respect to time between a and 0. So pretty straightforward. Let's do a quick example. We have an initial position of 9. We want to find our position at t equals 1 and at t equals 5. And so s at 1 minus s at 0 equals the integral from 0 to 1 of v of t dt. We can plug this into our calculators, or we could figure it out. But what we know is that this is equal to 35. S of 1 minus 9, which means that we have moved a total of 35 units since we started counting. But it also means that my position is equal to 44 units. And we can do the same thing with time of 5. S of 5 minus S of 0 equals the integral from 0 to 5 of V of t dt. And what we get is, oh, I wrote down the wrong numbers. Oh, gosh darn it. Okay, sorry. 35 was actually the answer to the next one. This was actually negative 11 thirds. And therefore, the position at time 1 was equal to 9 plus negative 11 thirds, which is 16 thirds. Notice that we actually moved to the left because 1 is less than where our velocity went to 0 and switched directions. And this one is 35, which means that S of 5 is equal to 44 when we add the 9 to both sides. All right. Sorry for the confusion. Was just looking at my notes. Why don't you go ahead and do exercise 1, but only do parts A and B. And I will see you back here. Do I want to do one more example before I stop this video? Yeah, let's do a quick total distance traveled example. And then we'll call this one quits. This is example 3, and this is a little bit different in that it is distance traveled. Now you have to be careful because displacement is where are you relative to your end point. Position is relative to where you started, so you have to add in your starting point. But distance traveled is going to be the sum of the absolute values of all of those rectangles. So all those red rectangles that you saw back here, if we're talking about actual distance traveled, we actually traveled that distance. We don't want to take that off the calculation, which means that my total distance traveled in that first 5 seconds will be the integral from 0 to 5 of the absolute value of V of t dt. And you can just plug this into your calculator, or you can just find the anti-derivative and use the fundamental theorem of calculus. What you get is you get approximately 42.59 units. And the big thing to remember is do not forget absolute value symbols when you were talking about distance traveled. Okay. Go ahead and finish up with exercise 1C, and we'll see you in the next video for a quick general strategy and another example. Thanks for watching.